Hello chemistry students. Hey, we're about to start unit 4, which is about electrons in our modern atomic model. So this is lesson 4.1, where we're going to look into the nature of light, and this would go with the readings in textbook section 5.1. So the objectives for the first lesson, we want you to be able to use the mathematical relationship between wavelength, frequency, and velocity for electromagnetic radiation, and to use the relationship between frequency and energy in electromagnetic radiation, and to relate frequency, energy, and wavelength to the various types of radiation on the EM spectrum, and to give the constant value for the speed of light or the velocity of electromagnetic radiation in a vacuum. So let's get started.
Alright, so first we're going to talk about the basic properties of light, and to look at a light wave, it looks a lot like a sine wave. And when we look at sine waves, much like in math, there are some normal terms that you'll hear. The first, I guess, we want to talk about, let's talk about amplitude. So the first we're going to talk about is amplitude, and that is the height of the wave. So you can see the arrow there. He's drawing in the amplitude. The next thing is the wavelength, and that is the measure between peak to peak or trough to trough. So right there would be the amplitude.
We use the symbol lambda for wavelength,
which is like an upside down Y.
Upside down letter Y. And
then to talk about this, we should also probably say what's a trough and a crest. He's just labeling the second way to measure wavelength. So, Mr. First, you'd mark a crest for me. At the top, it would be a crest, and at the bottom would be a trough. And we use these terms to talk about light and calculating their properties.
So light has a wave-like characteristic, and it has a measurable wavelength, and it has a measurable speed. And don't forget, waves move, so this thing would be traveling, so there's actually a measurable v, which stands for velocity, and that the velocity is another property of the wave and of light.
That's in meters per second for that velocity, but we can talk about all that.
Well, we're going to summarize all that down below here in wave equations and symbols.
And actually, according to de Broglie, everything in nature has a wavelength, but we're not getting into that just yet. It's the wave-particle duality theory.
Right.
So the first equation we're going to talk about, I guess, will be nu equals lambda f. Nu is like a V-looking thing, equals lambda f. That is the velocity of the wave equals its wavelength times its frequency. So wavelength was what we talked about up top here, where we have lambda. It goes from crest to crest or peak to peak. And the units for that is what? Nanometers, I think we usually use.
I think the
meters,
standard unit is actually meters, although it might be expressed in something
light's
else.
done in nanometers, but we usually calculate it in meters. Okay.
Calculations, it needs to be meters.
And frequency, its unit is called hertz, which is also known as 1 over seconds. So it's Hz for hertz, capital H, Mr. Ferguson. And 1 over seconds would be the units. And then,
so the frequency, just to understand, like basically if you stood in one spot, if I stood right here and I was watching this wave go by and I counted how many crests went by in a second's time, that's my measure of frequency. It's waves per second. So whatever per second.
We'll show you a good example of this in a second. The next equation we want to talk about is E equals HF, where energy equals HF. We did forget one thing with the nu itself. Nu, if you put that over there, is, of course, as we said, speed, or velocity. And its units would, of course, be meters per second. Alright, there we go. Now we can go on to energy. Energy is calculated using H, which is actually just a constant that was calculated through a lot of trials. It's called Planck's constant, and it's an H, and its value is always the same, hence the word constant. it's 6.6 times 10 to the negative 34th joules times seconds, or joule seconds. So once again, that is 6.6 times 10 to the negative 34 joules times seconds. And that's just a constant. It's always the same. And of course, frequency, as we know, so it's Planck's constants times frequency, gives us the energy of the wave. And energy is measured just in joules. And there's a lot of things we can talk about, how energy and frequency affects or are related to each other. It's probably something we should mention while we're here. That'll be on the next slide.
I think that is on the next slide. Now, one thing that you're also going to see as we go through this, in a vacuum, like space, where there's no matter in the way, the speed of a light wave is a constant. It doesn't matter. Any electromagnetic radiation, whether it's visible light or invisible light, travels at a constant speed, and that speed is said to be c. So c, you're going to see written as that's the speed of light,
which is 3.0 times 10 to the 8th meters per second.
Times 10 to the 8th meters per second. So you will sometimes see Mr. Hunter and I, or the text, use the equation C equals lambda F, where they'll just substitute in that constant value for C, 3.0 times 10 to the 8th. So that would be specific to light only, where the nu equals lambda F would be for like a wave at the beach or any other wave.
There's one last thing we should take note of. Notice there's an F in this equation and an F in this equation. That means you can combine these equations if you set them both to the same frequency. So if you have the speed of light and you have Planck's constants, you can sometimes solve for the equation in different ways, because, like I said, if you have something that's in both equations, you can set them equal to each other. But before we get into that, let's start talking about some more properties of light here on the next slide. So before we get moving here, please turn into your packets to page 3 for some of these notes, and then reference in your notes that you should look at page 3, because this slide here is the exact same thing we have in your note packet.
This is color, and the one in your notes is black and white. That's the only difference.
But this will help us explain to you the relationship between frequency, energy, and even color
wavelength.
And wavelength as well. So, Mr. Ferguson, let's first, I guess, look at the frequency here. This right here is, I guess, a good way to look at frequency. If you look at here first, this long open trough, and then at the end you see how close they get together. Which one, I guess, would have a higher frequency based on our definition of frequency we already gave?
So since we know that the speed of light is a constant, so the wave is traveling past us at the same speed, since this one is more stretched out, I'm going to say the frequency is going to be lower because fewer waves are going to go by me per second.
A few crests per second.
And over here, we're going to have more crests per second because they're closer together.
Exactly.
So
probably write that down somewhere.
So if we look at the frequency, it's already actually written here. So the frequency is getting, so as we go for the frequency down here at this end of the spectrum is 10 to the 4th hertz. And up at this end of our electromagnetic spectrum is 10 to the 20th hertz. So we can see that as we go across our electromagnetic spectrum, frequency is increasing.
And along with that, they don't really show it here, but the wavelength at the top, you can see it goes from radio to micro to infrared, visible, ultraviolet, X-ray, and gamma. You can see that as we go across, the wavelength is going from 10 to the 3rd, 10 to the negative 2, 10 to the negative 5, 10 to the 6th. That means they're getting a lot more compressed and closer together. So if you have a small wavelength, that means you have a high frequency. If you have a big wavelength, like radio waves, for example, you have, if you have radio waves with a large wavelength, it has a low frequency.
Okay, so we're going to look, the wavelength kind of increases in the opposite direction. So I think for us, that tells us that when we're talking about electromagnetic radiation, invisible and visible forms of light, long wavelengths, like radio waves, correspond to low frequencies.
Yep.
And short wavelengths like up here at the gamma end, 10 to the minus 12th is very short, correspond to very high frequencies.
So the next thing that you have to
So
correlate...
they're opposite to each other. Go ahead, I'm sorry.
So the last thing we have to correlate here is energy. You don't actually see energy written anywhere on this chart, but energy, as we know, we can calculate it. So he's writing down the equation for energy. So as you increase frequency, according to this E equals HF, as you increase frequency, you'd expect the energy to increase.
Right, so, because H is a constant.
Yeah, so as F goes up, E goes up.
So if the value of F is bigger, the value of E is bigger, so we're going to put energy down here at the bottom.
Yep, and it just increases as frequency increases. It decreases, though, as wavelength increases. So these are some, I would say, these are some things you need to learn. There's some patterns here.
There, and I think if you kind of put those arrows on there the way that I did, they'll help you kind of recognize... That'll help you recognize the patterns. And the last thing that I think we want to point out, and I'm sure you probably hit on this in Earth and Space Science, but this entire spectrum, that we call it, is all of the different energies, frequencies, wavelengths of electromagnetic spectral energy. And a lot of times we'll use the term light, and all of these are of the same form of energy, but the more proper term would probably be electromagnetic spectrum energy. So at this end of the spectrum, the one extreme is radio waves, and they have the longest wavelength and the lowest frequency and their lowest energy. So this is how your cell phone talks to other cell phones, how we receive Wi-Fi signals in our house is different frequencies on this radio wave spectrum. Stepping up a little bit, then we have microwaves, a little bit higher frequency, a little bit shorter wavelength.
Microwaves are the ones we use to cook water with. It causes vibrations in water.
And stepping up a little bit more is infrared, which is actually the root of the word means below, the prefix infrared. It's just beyond what we can see, and this is like those heat lamps in restaurants.
Yeah, I believe infrared's also used to excite the electrons in
can be, yes. And then in the middle, what you and I would refer to as light is just this very middle part of the spectrum, kind of right in here. Okay, and this is our Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet.
Which is blown up here on the bottom here.
And that's right. So they've just taken this and kind of stretched it out. You can see that's the visible spectrum. And then as we move up above the visible spectrum to, again, we can't see this either, ultraviolet. Now we're at a higher energy. This is what gives you a sunburn.
Yeah. I would like to correct my previous statement. It is microwaves that moves water molecules. It actually causes friction between them. Infrared causes the vibrations of the bonds to be changed, and then ultraviolet is what excites the electrons to change energy states. So that's something that might actually come up later, but it's not. It's just something I want to get out there. I don't want to be recorded for all history as being that guy who mixed that up.
Yeah, he's the wrong one. He was wrong.
Yeah, now I have it right.
So then as we're increasing in energy, as we increase in frequency and we decrease in wavelength, so these are your high energy end of the spectrum. X-rays, they're very high in energy. They'll penetrate a lot of things. If you get an X-ray because you broke your arm or to get your tooth filled, those X-rays are actually going right through you.
And the only reason you can see your bones is your bones are a lot more dense than your...
They block a few of the X-rays and the rest of your tissue doesn't.
And if you're the Fantastic Four and gamma rays, you get turned into...
These are the ones that turn you into a superhero.
Or kill you in the most horrible fashion
Most often
possible.
They would kill you. So these are extremely penetrating rays. And highest in energy and shortest in frequency.
Cause cancer, cook you, etc. So let's do some practice problems with these.
So we're going to go through a few example problems, and then
we'll have a lot of practice.
We'll have lots of practice in class. But copy these down. This will give you a kind of an idea how we approach this kind of problem.
And do be aware that you will have to perform algebra to solve these equations.
And use units.
The triangle is not your friend. It's a crutch. Try to stay away from it. I know they taught you to use the fastest way possible when solving for things, but in science we try to go for understanding, not for speed. Yeah. So let's take a look at this. Okay. First we want to find the wavelength. So find lambda if we have a frequency of 1.00 times 10 to the 14th hertz.
So I'm going to use the equation V equals lambda times F. But remember that since we're dealing with light here,
Light in a vacuum.
So we can change that to C, which is a constant, equals lambda.
If it's not said in a vacuum, you can assume it's in a vacuum.
We're going to assume it's a vacuum and that the light speed is constant. And now I want to find wavelength, so I'm going to solve this equation for wavelength by dividing both sides by frequency, which will divide it out here. And then my equation becomes frequency is the speed of light divided by the wavelength.
Exactly.
Okay, so I substitute in, if you remember the value of C, 3.0 times 10 to the 8th meters per second. That's a constant. That's always going to be the speed of light in a vacuum. We're going to divide it by our given wavelength, which was 1.00 times 10 to the 14th. Now, the unit might throw you off here a little bit. That's hertz, but remember we can replace hertz with 1/second or just per second. So we have per second in the numerator and per second in the denominator, so the per second divides out. And the only unit that we're left with then is meters. So that's going to carry through into our answer.
And the last thing you have to look at is to figure out how many sig figs you need. But since C, speed of light, is a constant, we do not count that towards
That's
sig
right, it
figs.
has infinite sig figs.
So the only thing we look at is the bottom number, which has 3 sig figs. So our answer is going to be 3.0 times 10 to the
3.00
times 10 to the negative 6th
times 10 to the minus 6th meters.
I was trying to count some sig figs here. We're trying to count some
So
zeros.
now if we wanted if we wanted to look on our spectral diagram, then we could figure out what wavelength that would correspond to, whether we're dealing with visible light or whatever. And we'll practice that in class too. But that's how you approach that problem. It's just solve the equation, stick in the constants and variables,
basically
and then
a plug, chug, and end.
Work it out.
All right, so the last one here we're going to do with you. So we have a lot of practice the next day. So now we have an X-ray with a wavelength of 1.3 times 10 to the negative 10th meters. We want to find energy. So the first thing we need to do is...
So I'm going to say, well, all right, so we're going to find energy. Well, I already know the energy equation, E equals HF. Uh-oh, Mr. Hunter, wavelength doesn't show up in this equation.
So either we have to do a two-step problem, or we're going to have to combine two equations together here.
Let's do, my brain can only handle one step, but let's do a two-step problem.
So let's plug in the C equals lambda F.
C equals lambda F. So like Mr. Hunter mentioned before, we've got the same variable showing up twice. So that's our key to get from one relationship to another. So we're going to use the same equation we did up here to find the frequency first of all. Okay, so we know that frequency is going to be C divided by wavelength, which is 3.0 times 10 to the 8th meters per second, divided by 1.3 times 10 to the minus 10th meters. Okay.
I got, again, 2 sig figs for this one, so I got 2.3 times 10 to the 18th for the first part. 2.3 times 10 to the 18th.
So the frequency is 2.3 times 10 to the 18th per second, or hertz. Okay.
Now we plug that value into our E.
Is H times F.
We take that value and multiply it by Planck's constant.
So I'm going to bring in my F, which is 2.3 times 10 to the 18th per second. Times Planck's constant, which was
6.6 times 10 to the negative 34th.
6 times 10 to the minus 34th joules times seconds. So we have seconds over here and per second there. That divides out.
Yep.
The answer will come out to be just in joules.
The answer will be in joules, and it's 1.5 times 10 to the negative 15th.
1.5 times 10 to the negative 15th joules.
All right, we'll have more practice with this soon. So if you don't understand it yet, we'll have plenty of practice, and we'll see you tomorrow.
And by the way, people, Mr. Hunter and I, in hindsight, well, it was mostly me, just realized I screwed up when I was up here. Actually, the first example problem, when we wrote the equation here, this should be lambda over here, and this should be frequency down here. So we did the math right over here. Yeah. I just didn't carry that over to here. But then we actually did the math. Right. We plugged it in right, and we have the right answer. The units canceled out correctly. Just there was a little glitch right here, so that probably confused you. Apologies for that. We'll do better next time.
Now have a good night.
So to finish the lesson, what we'd like you to do is to answer the following post-video questions. The first one, we would like you to find the frequency of light with a wavelength of 7.3 times 10 to the minus 6 meters. So of course, to do this, you're going to need the equation C equals lambda times F, and I wrote it there, except that the lambda, I don't have a key for that. That would be that upside down lambda. Sorry for the horrible writing. So you're going to need the answer from number 1 to do question 2, which is you're going to use the Planck equation to find the energy of a photon of light from problem 1. So of course you're going to find the frequency in problem 1, then you're going to use the frequency in the Planck equation to find the energy. Good luck.